Hey, Mike, just wanted to let you know I did get your email.
Perfect. We may have, let's see, I did that yesterday. We might have one more in the streaming. I just got an email about adding the class, but other than that, it should be closed.
Okay, I usually add them in if I start getting multiple people.
Cool. All right.
Multiple days of people I don't have on the list.
Right. So where we left off last Thursday is we were talking about interpreting the histogram, right? And I'd written up like 3 different things. The first thing was we want an overall pattern, correct deviations. That's fine. What we were really interested in was number 2 and number 3. Number 2, we always want to talk about, right? So I'm going to do it like this. Number 2, we always want to talk about shape, center, and I always use the term spread. We're talking about variability. And then probably the last thing I had written down on Thursday was, okay, I'm going to give you some ideas here in a minute about different shapes we'd like to talk about. There's 3 of them we like to see if we have that shape. The center is this 50-50 area point, right? We want a point on the x-axis where we'll cut the area of the bars in the half and half. And then the spread of the variability, I told you we couldn't do very good. The best we could do is just give me the smallest and the largest values that we see, right? And then the third one is You know, those striking deviations we're going to talk about are outliers. Those are something that is, look, you're looking at a histogram, right? And so an outlier would be something, would it be an individual observation that is much larger or much smaller than all the rest of them? In other words, they're stuck out here by themselves, right? For some reason, they have a much larger value or much smaller value, okay? I'd like to focus in on the beginning of class here today with this guy, because there's like 3 shapes we like to talk about, and the first one is this. So I'm on page 25 in your text. All right, there's a little box there, and we're going to talk about symmetric and skewed. So the first one we'd like to talk about, and it's probably end up being our most favorite, is symmetric. And then if I forget, I like to put the word, roughly symmetric, because normally things aren't perfect, all right? So, unless I get to just draw the picture however I want, okay? And what it says is, the definition in your little box there says that a distribution, we say that a distribution or a histogram is roughly symmetric or symmetric if the left-hand sides and the right-hand sides are mirror images of each other. And what that means is, if I got my histogram on a piece of paper, and I can find the center of it, and if I could fold that piece of paper across the center on top of itself, the left-hand side would lay on top of the right-hand side. All right? So, the standard picture I have here for symmetric is, all right, so I'm looking here, would be something like this. Now, I'm drawing it nice. We would say that has a single peak to it. It's got a single hump. You might hear the term unimodal. What does that mean? It means it's a single peak that has a single hump here. That is something that is roughly symmetric. And so my question is, what do I mean by the left-hand side and the right-hand side being mirror images of each other? Where in the hell is the center at here? In other words, where's this point on the x-axis that half of the observations are smaller and half is larger, meaning half the area to the left of this value and half the area is to the right? Well, I would expect the center to be somewhere like here. Well, hell, it's roughly symmetric. I would expect right in the middle for, half to be smaller and half to be larger because, left-hand side and the right-hand side are mirror images. And so what I do is, I do it like that so okay, the center is this value that's on the x-axis, right? But if I could draw this line, if I could fold that piece of paper on that line, right, with the left-hand side and the right-hand side lie on top of each other when I looked at it, yeah, that's what we mean to be roughly symmetric. The center is about in the middle of your picture there. Put it this way. It's about in the middle of your histogram, right? Okay? Now, here we're talking about a histogram. It's roughly symmetric. I've shown you what a picture of one roughly symmetric is. Well, I warned you last Thursday that there's always 2 things going on. We start describing our histogram by giving a shape like roughly symmetric. And then what is that telling me about the distribution? Well, what it's telling me about the distribution is, you do understand that the majority of the values are here, right? In the middle, right? Roughly in the middle of the range of values that you're seeing. Everybody follow that, right? So when you tell me something's roughly symmetric, what I know is, the way I'm looking here, the majority of them are in the middle, right? They take values in the middle. I also see that as I go that way, and as I go that way, there are fewer and fewer values. Right? So in other words, as the value of my variable either increases, that would be increasing that way, right? Or decreases, going that way, there are fewer and fewer values out here in these tails. The majority of them are sitting in the middle. And then as we increase the value or we decrease the value, there are fewer and fewer observations. So all that I have there in blue That's telling you about the distribution, right? The majority of them are in the middle, right? And as I increase or decrease, there's fewer and fewer of them. That's roughly symmetric. That's pretty much, you ask me to draw you something that's roughly symmetric, that's the one I'm going to draw you every time. Okay? 2. We'll start with this one. Skewed right. People may say right skewed. I say skewed right. I may use the other one on you too. And what that means is we have a tail to the right. So what does it mean when I'm looking at a histogram and I say, okay, well the shape there is skewed to the right? What it means is it would look something like this. And I'm going to exaggerate it so it looks like what I'm talking about here. There's your tail. All right? So that's something that would be skewed to the right. Tail's going to the right. Now, where's the center at here? Where's this 50-50 area point? I'm going to give you, obviously it's not in the middle of the picture here like with roughly symmetric, right? The center should be somewhere around, if I think about the area of the bars and trying to divide this area up into half and half, I'm assuming that we're somewhere around notice when it's skewed to the right, the center is actually to the left of the middle of the picture, right? Okay? Now, what does it mean for me to tell you that your histogram is skewed to the right? What does that mean in terms of my distribution? Where's the majority of the observations this time? It's on the low end of the scale, right? The majority are actually on the left side of the histogram. And then what happens? As we increase, what happens to the number of observations? There's fewer and fewer because you have that tail going out to the right. I'm going to scream this at you one more time. It's skewed to the right, not because of where the majority of the observations is, it's because of where the tail goes. The tail actually goes out to the right where we get more and more observations, right? We increase, there are fewer and fewer. We got this tail going out to the right. The majority are on the low end of the scale. All right? Well, if they're skewed to the right, there is skewed left. Where's the tail? Well, if it was skewed to the right, the tail went to the right. This time I have a tail to the left. Okay? So when I would draw you this, what I consider to be the standard skewed to the left, it's just the opposite of the one I just drew for you. Where would the center be here? Where's that 50-50 area point? I'm going to give you, it's not in the middle of the picture. It actually has to be a little bit to the right of the center. I have about half the area to the left and about half the area to the right if I start stacking these bars up. Where's the majority of the observations in my distribution? They're on the high end of the scale. And what happens as we decrease the value of the variable? There are fewer and fewer observations that go that way. These are my 3 standard shapes here. With all 3 of them, I've shown you about where the center is, right? You know, we got roughly symmetric, skewed to the right, tail to the right, skewed to the left, tail to the left. Now, what I want to do is this. I want to come back here to this problem we were working with last Thursday where I showed you at least a little bit of it making a histogram by hand. I got Minitab to make the other part of the histogram, right, to make the whole thing. It was the ones where we were looking at this example 1.4, I think it is. We made a histogram of the percent of state high school students graduating on time. I want to come back to that and get that one up here for you because it's easier for me to see it here. than me making something for you by hand. So I've got these mini-tab files. Remember, I have to go and find users, me, desktop. I have these on the desktop, and this was example 1.4, the graduation rates. Remember, that's just a nice way for me to get this table 1.1 on page 22 in there. All 50 states are there, and the District of Columbia. And what do we have? We have the percent of graduates that are on time. We made a histogram last week. I'm going to show you again. Graph, histogram. We just want a simple one. It's already highlighted for us. It wants to know where's the variable at, and the variable is in column 2. We can double-click that. And then I don't screw with anything at this point. I just click OK. It's going to give me what it gives me. Remember, what it gives me is it marks in the middle of the bars, and I told you that was the one thing I don't like, right? So I always come here, double-click on the x-axis, go to binning, cut point. What does that do for me? At least it makes it marking, at the edge of the bar, right? So I can read it. Okay? Now, the problem with this and what we did last Thursday when we did it by hand, and the book talked about it, they did it with 5, right? Here we did it by 2.5. Minitab picked for us. Well, I'm not going to start changing shit back there. I'm going to use what Minitab gave me here. All right? Now, let me ask you this. If I was looking at this and I was to ask you the shape here, what would you tell me? That's damn straight, right? That's skewed to the left. Right? Don't I have a tail going out to the left here? You see it? Right? So we would definitely say that's skewed to the left. What does that mean to us here? The majority of states have their graduation rates of students on time is between what? I'm going to say 80 and 90, right? That's where the majority is. Here to here. The majority of the states have between 80 and 90% of their graduates graduate on time. Look, I know you can see that skewed to the left. Hell, I know you can see that tail. But then you got to take that one step further. What does that mean in terms of my distribution? It means the majority of them are on the high end, right? And as the value of variable decreases, there are fewer and fewer states there. Everybody okay with that? All right? So, the majority are between 80 and 90. And what do we know? As the percent of high school graduates that graduate on time decreases, what happens to the number of states? There are fewer and fewer. Yes? Okay? Now, what are we going to do about the center? Look, I can tell you really easily here that if I come over here and I tell you, okay, what I'm looking at here is example 1.5. If I had to pick here and I had to tell you about the shape, the first thing you would tell me is it's skewed left. Right? We like to talk about that. The other thing we like to talk about is how many humps do you have? How many, peaks? Now, they don't have to be the same heights peaks, but what I have here is I would say this is single peak. People might use this term on you interchangeably. If it's me, I'm talking about single peak, and some statisticians talking to you, they might be using the term unimodal. Unimodal means it's single peak. Look at it. There's your single peak. All right, there's your unimodal. It's skewed to the left. I got a tail going out to the left. Okay? Now, I'm looking at your example in the book. Shape. The distribution of single peak, that's the ones from 85 to, in this case, 92.5. The way we have it drawn, right? The majority are between 80 and 90. I want to get that stuck in your head too. That's how you think about it. It says the center. Now, your dude cheats in the book here. I'm in chapter 1, and he's going to use shit in chapter 2 out of you. All right? Here's what I would like to come to an agreement with me and you on. We're going to do a much better job in the next chapter to actually calculate the center, right? We're going to show you a calculation to find the center. Here's what I want to know. Where do you think the center is? I mean, I don't care about an exact value. Do you think it's like to the right of the center or to the left of the center? Oh, I'm asking bad, dumb questions now. You understand, if I had to be really picky here, I'd say the center is somewhere around, yeah. Because think about it like this. What we'd be doing is we'd be stacking the bars to the left and stacking the bars to the right to see if they stacked up about the same. Remember, that's going to be a little bit over there. So look, can we agree that the center is somewhere between 80 and 85? And just call it a day? Until we get to where we can actually calculate better than that, just tell me, look, I would never give you this question on a test and for you to tell me that the center here is, let's say, 83. That's not fair, right? If I had 83, my other answers would be 97, 16, 32, right? You need to know it's somewhere between, I'm just being nice here and saying it's somewhere between 80 and 85, right? So that's the way I'm going to leave this over here. When you tell me that and I'm looking for the center, I don't want to get really picky here and drive me and you crazy. The center is between 80% and let's say 85%. As long as you knew that much, that was about where this 50-50 area point was, and about half's less than that and half's greater than that, I'm very happy. All right? To pick out the precise one, just looking at a histogram, there's no way in hell. I need chapter 2. Now, what about the spread or the variability? And I'm going to give you two options here, depending on what is given to me and you. Sometimes, the data, let's say like table 1.1 is given to me, and I can be exact. But sometimes all you're going to have is this. Right? I mean, when I look at this, I don't know that anybody has 63%, 61%, 76%. I don't know that. I just know how many's in each one of these little 2.5 width classes, right? So if I'm looking at your histogram, the best you're going to tell me is, what's the smallest possible? 60. What's the largest possible? That's 92.5. Remember, we went by 2.5. So I'm going to give it to you like this. If you're looking at the histogram, the best we're going to do is 60% to 92.5%. Right? You're not going to know the exact value. It's just what's the smallest possible, what's the largest possible there. But if you have the data, in other words, the data is going to come to you in some kind of maybe table, like table 1.1, can you give me the exact value then? And the answer is, yes, you can, because we'll know what the exact values are. And the exact values are, they range from 61.4% to, I'm cheating, 90.5%. You're going to get different answers here, whether you actually have the actual data or whether you're reading the histogram. Is everybody okay with that? That's the reason I'm giving you both of those, because a lot of times, all you're going to have is the histogram. What's the smallest, what's the largest? Sometimes you'll end up having the data, and you can just look through and find it. Okay? Everybody okay with this? That was our first go at taking one of these, talking about shape, center, and spread. Now, you remember there was a number 3 there, right? Shape, center, and spread were always on the same line. And then there's this fourth thing. And my fourth thing here is, I'm going to put a question mark there, right? Are there outliers? Are there any observations here that seem extreme one way or the other? Well, I mean, I want to be fair here. I'm going to come back here and look. I'm going to clear this ink off, and I'm going to circle one of these for you. That's what I mean by being stuck out in the tail by themselves, right? I mean, if you think about it, if I look at this part, I'm not going to change my thought any. I'm still going to tell you skew to the left. The center's about where it is. Yeah, the outlier might actually be the smallest value here, but you see how there's these gaps? Right? So there's like, at least what I know is, whatever that one is I have circled in red, it's at least 5 percentage points away from the next one, right? This is what we mean by being stuck out in the tape. Okay? So then the question is, it seems like we have this possible outlier, right? Now, if I'm sitting here in Minicab, I can put my little cursor there. Maybe I don't like my ink. So I know there's one in there, right? There's something between 60 and 62.5%, right? So I'm reading that bar value. They're telling you the highest one, and then the bin is telling you the class is from 60 to 62.5. There's one in there. Well, do you remember my smallest value I had, 61.4 or something like that? Who is that? So what I see is, I've got a possible outlier, 61.4. I always say possible. I'm going to do better in chapter 2. Okay? Now, which one has 61.4%? Well, if I look at the table on page 22, the one that has 61.4% is oh, shit. District of Columbia, isn't that a city and not a state? Yeah? Yeah. Now, look, there's no way in the world I was going to know that this one that's over here that's between 60 and 62.5 was the District of Columbia was 61.4. I actually had to go find the data, right? Or I guess I could have looked at it right here. District of Columbia, number 9, 61.4. Okay? So I have this possible outlier. It's the District of Columbia, 61.4%. All right? Now, here's the problem with me and you and outliers. Everything me and you're going to do this semester, if there's outliers in the data, we have to make a note of that. It kind of messes with us. So we want to pay attention to see what's going on here. And then, when I see who it is, are you shocked? Don't you imagine like there's a lot of people moving in and out of the District of Columbia? Are you shocked at the graduation rate? Remember how things were calculated here? It didn't take into account for that. Okay? So, my first thought is, yeah, District of Columbia, it probably is an outlier here. But remember, it's a city, not a state. In other words, there's something special about it. It's actually different than the state, right? It's just a city. So you always make a note of, okay, so this is an outlier. What's up? Well, here's the District of Columbia. It's a city and not a state, right? So there's some special nature about it. There's something special about it. I'm not shocked when I'm thinking, okay, it's a city and not the state, and what city you're looking at, that the graduation rate is so low. All right? I'm not shocked by that. Now, here's the thing. Are we okay with all 4 things I did for you here? Remember, well, the way I'm doing it is I'm looking here. I see a tail. I see single peak. We made a guess about the center. We kind of eyeballed it. Smallest and the largest, I gave you options. If you got the data, be exact. If you got the histogram, you're only going to be so perfect. And then, is there anybody stuck out in the tail? Is there anybody to the tail to the right? No. There's definitely one to the left there, right? So that's the reason we're picking that one out. We're calling it a possible outlier. District of Columbia, shit. It's a city, not a state. It's a special. Okay? Now, before we do any more of these, I got the following thought. Okay? When you're talking about possible outliers, stuck out in the tail, much larger, much smaller than everybody else. All right? First off, think. 1, did we make a mistake? it's going to be rather hard for me and you to make a mistake when the data is given to me in a file. I mean, shit, for all I know, they could have done a typing error. I would hope not, since that's out of our control. It could have been okay, they just wrote it down wrong to start with. I would hope not, because that's still out of mine and yours control. Right? You know, that something got typed weird in the Minitab file, or somebody recorded something wrong. You know, did somebody make a mistake? Normally what me and you are worried about, because those shouldn't be a problem for me and you, is there a special nature about it. Like we're looking at a city instead of a state. All right. So DC is this city compared to the states there. Now, I've thought about everything I can think about to tell you, right? Shape, center, spread, variability, outliers. That's it. That's the way we want to describe a histogram. And when you're describing the histogram, you're telling me about your distribution. Now, I'd like to look at this one here, example 1.6. Again, I want to get a little bit of practice with Minitab and looking at different shapes here. So in 1.6, we got Iowa test scores. It says figure 1.7, which is on page 27, displays the scores of all 947 7th grade students in public schools at Gary, Indiana, on the vocabulary part of the Iowa test of basic skills. So what you have here is you've got 947 7th graders. Gary, Indiana. Okay, we like to keep track of the individual, the who. What did we measure? We measured the vocabulary score on, what was it, the Iowa test of basic skills. That's your variable. It is quantitative, right? So what I want to do is I want to come over here. I can see in my textbook that there's a file right here next to example 1.6, and the file was Iowa test. So we're going to get rid of this one. We're going to come here, we're going to find that file. Maybe. Oh. Iowa test, example 1.6. That's nothing more than all 947 vocabulary scores on that test. I want to make a histogram. Simple. Where's the variable? It's in column 1. We're going to click OK. Now, there's something I want you to notice. The left-hand side is giving you the count, right? The frequency. And then across the bottom is the scores. Remember, I never like the, that's just me, I don't like that midpoint. I like the cut point. I change that. Everybody okay with that, right? All right? So, if I had to pick, you know, I always start with the shape. What's the shape here? See, that's as roughly as symmetric, as nice as we can get when we actually measured some variable like this, right? So, if I had to pick here with this example, I'd be telling you your shape is roughly symmetric. How many peaks was I seeing? See, when I'm doing this, I'm big picture thinking. In other words, I see like a single peak again, right? About in the middle. So it's a single peak. I'm going to give you this other term again. You might see unimodal. That means single peak. Okay? Now, I got to come back here. Where's the majority of the observations here? Well, it's roughly symmetric. They're in the middle of the picture, right? It looks to me like the majority of the observations, and I'm just going to pick a spot to go here. I'm going to go from 4.5 out to 9. right? So the majority of the students scored between 4.5 and 9. What else do we know? Is as the value of the variable increases and decreases, we fall off, right? I think about the tail going down, right? Roughly symmetric tells you that stuff. I just want to get that stuff stuck in your head about the distribution. Okay? Now, where's the center? It's roughly symmetric. Where would we expect the center to be? Somewhere in the middle of the picture, right? Somewhere in the middle of the histogram. Yeah? I'm pretty close. Now, let me ask you this. What's my class width here? I mean, I know you're only marked at 3, 4.5, 6. That's not the class width. What's the widths of the bars here? 1/2. Look, there's always a quick way to cheat if I'm looking at Minitab. And I didn't mean cheat. There's always a quick way to find this. Pick a bar. Pick the tall one. Maybe. And the reason I say there's a quick way, well, I can see the bar value is 152, right? There's 152 in there. You see where it says the bin is 6.5 to 7? It's telling you the class width is 0.5, right? Okay? So, can we all agree that, like I said, I'm thinking somewhere here. In other words, it looks to me like my center somewhere around 6.5 to 7. And I wouldn't even hold you to that. I'd have been good if you told me from 6 to 7.5. Remember, we're eyeballing it. But it's somewhere between 6.5 and 7. So the center is 6.5. All right, somewhere between them. I'd have been happy with 6 to 7. Anything you gave me around the middle there, I would have been happy with. Now, what about the spread? Now, I'm going to give you, the only reason me and you have the data is because we had it for Minitab. What is the spread here? Well, I have one out here, right? That's between 12 and 12.5. Then I have one down here, which is between 2 and 2.5. So if I told you the spread was without knowing the exact value. Everybody okay with that, right? And even if I didn't have the little cursor put on there, things would be blowed up big enough that you could see, yeah, it's 2 out to 12.5 because you could figure out that your class width was 0.5. All right? Now, let's say I wanted to be exact. Could I? In other words, if I wanted the exact numbers, what would I have to do down here? I'd have to scroll through here and find the smallest and the largest, 947 of them. Anybody want to do that? No, you can say no. Nobody wants to do that shit, right? No, but my question is could you? If I had them all listed for you, could you tell me the smallest and the largest? Yes, you could. Are we going to do that here? No, we're not. We're going to use the histogram here, right? We're going to say, oh, it's from 2.0 out to 12.5. Okay? Now, what about outliers? Now, we got to be careful here. Because, I see there's a gap here. Right? There's a gap there. From, what is that? That's 10.5, from 11.5 out to 12. There's nobody in that 11.5 to 12. And then how many was here? From 12 to 12.5? 1. 1. Now, you got to think about how wide things are. That means there's somebody between 12 and 12.5, and the next one is between 11 and 11.5, right? Is there a possible outlier here? Yeah, man. Right? Possible. Between 12 and 12.5. In that bin, in that class. Now, do I think there's a mistake typing it, a reporting error? Is there some special nature? I don't even know whose scores are, right? I just see there's somebody, maybe a possible outlier here, right? I can't really say anything about it, right? It's not like me before being able to pick out the District of Columbia. Here, yeah, there's a possible between 12 and 12 and a half, right? There's at least one gap there. One class is empty, and then there's another. Probably in the big scheme of things, it's probably not an outlier, but just make note that, yes, there's something here. Okay. We okay with that? So here's one where you are roughly symmetric, the center sitting in the middle. You might have a possible outlier, you may not. Okay? Now, we got to do one other thing here. And we got to do this other example that's in the textbook. Because I will have you brainwashed before the semester's over. When me and you look at a histogram, there's always one of these three shapes. Roughly symmetric, skewed to the left, or skewed to the right. Is it possible that me and you look at something that has no shape, it's irregular? And the answer is yes. And the one to look at here is this example 1.7. I'm going to find the data file. I'm not going to make this by hand. I don't want you to have to look at the one in the book. I'm going to go to File, Open. This is example 1.7, SAT percent. And I'm going to read this to you. It says, example 1.7, depending on where you went to high school, the answer, in other words, who takes the SAT, may be almost everybody or almost nobody. Figure 1.8, which is on the bottom of page 27, is a histogram of the percent of high school graduates in each state who took the SAT test. Now, you guys understand that, like in the state of Tennessee, what test you take? ACT, right? This is an ACT state. There are some states that are SAT states, and the majority of their students take the SAT test, right? In the state of Tennessee, what the majority of the students take the ACT, right? Okay? So, if I make myself a histogram of this, you're going to see something that doesn't look like anything good. Now, I'm going to do this. Remember, I don't like that. The picture I have here, Minicab actually does a better job than the textbook does of making this. Now, does this look like anything we just talked about? You see how it looks like there's two separate pictures on the same graph? There's that group. Let me ask you this. Those ones that I circled in red, what states are those? Are those ACT states or those SAT states? Notice we're measuring the percent taking it, right? These are your ACT states. Right? SAT states, you would expect a high percent to take those. You're wasting your time to try to tell me about the shape, the center, the spread, outliers, or anything, because what we have is you have a irregular pattern. What you have is you have two distinct groups. ACT states that I circled with red, SAT states that I circled in blue. What that means is you have this same quantitative variable measured on this collection of individuals, but look, let's make it real simple. You ignored a categorical variable, right? Whether it was an ACT state or an SAT state. What would be the best thing to do here is to back up and say, let's just look at the ACT by itself. Let's look at the SAT states by themselves. In other words, just make one of each one of those, and then you can talk about it, right? Because then you're comparing, you're looking at all the ACT states, then you're looking at all the SAT states. When you see these two completely separate pictures, it's trying to tell you something about the data. It's trying to tell you, you measured your quantitative variable on, look, there could have been three distinct pictures, right? On two or more distinct groups. You're wasting your time trying to describe it as is. That's an irregular pattern. It's trying to tell you, look, you had two distinct groups in your data. The ones in red, the ones in blue. as straightforward as I can make it, right? That's the deal. We don't talk about anything about the whole thing together. Now, let's go at this a little different way. And what I mean is, let's go at this as follows. So up until now, if I give you the histogram, you should be able to tell me the shape. You're going to get a little bit of practice about that from Thursday to next Tuesday. I'm going to give you some homework problems on Thursday, all right? Can we go the other way? And what I mean is, can we talk about variables that have a particular shape for their distribution? In other words, we've already seen ones that are roughly symmetric, those Iowa test scores. We've already seen one that's skewed to the left, the percent of graduates on time in the States. Can we think about this the other way? Before we ever measure anything, is there any variables that would come up that we would expect their distribution to, let's say, be roughly symmetric? Well, I'm going to go just down the road, down the list like I did before. Remember, symmetric means roughly. It turns out there's a whole bunch of different things we can measure that are roughly symmetric. And I'm going to make it very straightforward. Heights of men. Heights of women. Now you understand, that's separate, right? See, the thing would be is if I took everybody's heights here and measured all the men and women together and I put them on the same histogram, what do you think you'd see? Oh, you'd see two separate ones, right? You'd see all the women, you'd see all the men, and you'd be having two separate ones on there. Why? Because you've got the same variable measured on two distinct groups. But what about if I just look at all the men? I would expect that to be roughly symmetric. Women, I expect that to be roughly symmetric. It turns out that the weights and lengths of the same species, their distributions will be roughly symmetric, should be roughly symmetric. The example the book gives you is, if we measured the lengths of cockroaches. Yep, that's the reason I always throw it out there, because everybody wrinkles their nose. I wrinkle my nose sheet, and we all wrinkle our nose. But if we measured the length of like 1,000 of them, and we plotted that, you would expect the lengths of the cockroaches to be roughly symmetric. The length and weight of the same species we would expect. So heights of men, heights of women, something we could actually measure. Weights, we would expect that. Okay? That's pretty standard thought. Lengths, weights of the same species, we would expect to be roughly symmetric. Now, as we get away from roughly symmetric and we get to skewed right, and actually, if I made a perfect test, which I never do, and I looked at the scores on that test, I would hope they would be roughly symmetric, right? I'd have a big peak in the middle, the majority do between, let's make it nice for you guys, the majority would do between, let's say, 80 and 90, and as we got higher, we fall off, and as we got lower, we fall off, right? That would be perfect. That ain't going to happen. Skewed right. We have a lot for this one, too. Incomes. Household incomes, baseball players' incomes, football players' incomes, home prices. Right? Incomes. Any kind of incomes of the same group you want to talk about? Yes. Home prices. I would expect to be skewed right. Those one students never like to talk about. Oh yeah, the majority of us don't do so well And as the scores rise, there are fewer and fewer of you folks. That would be a hard test. We try to stay away from it. Okay? So any kind of incomes of all the same group, home prices, at least home prices in the same area, right? You know, it's like around here, what the majority of home prices probably range from, and I'm going to be, I got no idea, from 100 to 400,000, right? And then as we get out to 1 million, 2 million, 3 million, there are fewer and fewer homes out there, right? If we go to the beach somewhere, well, what happens? Well, that big majority just moves over, and, you know, the majority are between 1 and like 3 million, and as we get out to 10, 12, 15, 20, there's fewer and fewer. My hand's moving that way because that's that tail going that way, skewed to the right. Now, what about skewed left? Well, I have a harder time here. Well, I mean, I guess I could give you the percentage of one-time graduates in the 50 states in the District of Columbia were skewed left. An easy test. Why? Then the majority of the scores have ranged from like 80 to 100, and as the scores went down, there's fewer and fewer students. And then the other one I have here is the date of coins in your pocket. Are most of them newer? Very few older and older coins as we go that way, right? So we're thinking about the date. I always shoot for, and every year I get more serious about this one, the age that I die. I'm hoping the majority of us live from, but when I was like 40, I was just hoping from 70 to 80, right? But now that I'm getting older, I'm thinking I'd like to live maybe to 90 to 100, and there's fewer and fewer of us die young. I always hope for that. Okay? So at least we've given you something about, when you see that kind of variable, this is kind of what we expect. All right? And then remember, don't forget about the SAT scores based on all 50 states. We're seeing something that's irregular there. Okay? So students want to know, how does that play a role? How do we ask you questions about this? And so I want to come to one of the homework problems here. I mean, I haven't went to any of your homework yet. You know, we've just been talking. And I come over here, and I'm on page 37. At the end of your chapter, there are some check your skills, and there's some multiple choice questions there. And then there's some exercises, which is you got to work things out. The one I wanted to look at is 122 on page 37, just for the sake of things. All right? I'm going to read it to you. And what it says is, you look at real estate ads for houses in Naples, Florida. There are many houses ranging from $200,000 to $500,000 in price. The few houses on the water, however, have prices up to $15 million. The distribution of house prices will be in words, they're trying to tell you the majority, right, range from 200 to 500,000. But the ones on the water, you know, in other words, as the value of the variable increases, as the home prices increases, there are fewer and fewer houses out there that range out to up to 15 million. What are you expecting here with this problem? They're going to give you your three standard answers: skewed to the left, roughly symmetric, skewed to the right. I put an arrow next to it, right? It's home prices. That was the example I had in my head when I'm trying to explain to you about how I expect home prices to be skewed to the right. That's it. And you're going, really, somebody would ask me a question like that? Yeah, I've seen that question show up on the final. So, that's like a pretty standard question. You know, we talked about it. We talked about it there. Seems like a reasonable thought. Now, the other thing me and you need to talk about here, all right, is we got another graph. Remember, a histogram is supposed to show you the distribution of your quantitative variable. Well, the other one is, for a quantitative variable, it's something called a stem plot. Sometimes you'll see stem and leaf plot. Now, the thing about a stem and leaf plot, I'm going to show you partially how you do it by hand. We're going to get the software to do it for us. But if I got to do it to hand to make a stem plot, it's even more work than, let's say, your histogram. Because I have to touch every piece of data. And so what I'm looking at is I'm on page 29. I'm going to look at this little bit here. What's in the box? It says to make a stem plot. The first thing we have to do is separate each observation, each value from your data, into a stem and a leaf. The leaf is the rightmost digit, and the stem is everything that's left over. All right? It says, write the stems in a vertical column. I'll show you that. My thought is I have to touch every piece of data. It's a quantitative variable, so you're looking at a number, right? You take the rightmost digit, that's going to be your leaf, and then everything that's left over is your stem. So I want to look at this example 1.8 here, making a stem plot. Okay? It says table 1.2, they're going to change the date on us. They're not going to be looking at these one-time graduates anymore. Presents the percent of adults aged 18 to 34 who considered minorities in each of the states in the District of Columbia. There's 51 individuals here. It says to make a stem plot of these data, first write the percentages 8 and 9 and so on and so forth. Here's my thing. I'm on page 24 and I'm looking at this table. I'm looking at table 1.2. What it is the percent of state population aged 18 to 34 who are minorities. The 50 states in the District of Columbia, there's 51 individuals. So for me to start making stems and leaves, all right, take Tennessee, for example. You see where Tennessee, even if you don't have a book, I'm going to tell you, Tennessee, the value is 30. Right? In other words, 30% of the state of Tennessee's population aged 18 to 34 is considered a minority. I need to make a stem and I need to make a leaf. Well, there is my leaf. There is my stem. Let's take a look at another one. Take one, let's say, like California. I'm just picking. I'd have to do it for all of them. California has 67. There is my leaf. There is my stem. Everybody okay with this, right? Now, I want to pick one other one here. And I want to pick one that has a single digit. And I'm going to pick West Virginia. Right? So it turns out, in West Virginia, 9% of the population between ages 18 and 34 are considered minorities. Now, if I have a single digit, how am I going to make a leaf and a stem? Okay, we're going to do the thing that we never do and you never write. Isn't there a 0 out front there that we don't write? Yes. We're going to put the 0 there, and here is going to be my leaf. Here is going to be my stem. So again, when you have single digits, put the 0 out front of it that nobody writes. The 0 is going to be your stem, and the 9 is going to be your leaf. Now, I'm going to assume, looking at this really quick, obviously the lowest stem you're going to have is a 0. West Virginia is not the smallest, actually. Vermont's the smallest. And the largest one is, I was picking California. There's Hawaii, New Mexico. Where's Arizona? It looks to me like I can go from 0 through 7, because Hawaii is the highest one, right? So what you would do is this, just to show you by hand, is I know when I'm all said and done, the stems are going to go from 0. I'd write them all down from the smallest stem to the largest one, going by 1 here, whether there's anybody on any of these or not. I draw a line. Okay? Everybody okay with that? Now what you do, I've got 51 pieces of data, I've got all these stems, and I got all 51 leaves. You put the leaf on the appropriate stem, but you put them in increasing order. So if I look here, the 0 is going to have, Vermont has a leaf of 8, West Virginia has one of 9. They go out there in increasing order. All right? Then, I'm not going to do the ones. I'm definitely going to cheat here because there's a whole bunch of them with ones. And when I say am I cheating, I am looking on page 30 in the margin. There are, somebody had an 11. There's a 5, 5, 6, 7, 8, and 9. If we touched every piece of data, you'll keep going, and the last one you'll put there is your 5. Let me ask this. When I'm done here, how many leaves should be on these stems? There better be 51, right? One for each one of the individuals in your data set. Okay? Now, there's something we need to keep track of here. Even if we're doing it by hand or we're getting the software to do it, the leaf unit. In other words, how did I chop things up? Where did the leaf go in the actual number? It was the ones position, right? Look. My numbers look like 30, 67, 09. The leaves are in the ones position, right? And the stems are in the tens. I want to keep track of your leaf unit. Where did everything go? Well, the leaf unit here is in the ones position. Why do I care about that? I can recover the actual data. Can everybody see that? Oh, somebody must have had 0.8, right? So somebody had 8%. I don't know what state it is, but I know that value. Can you see that somebody had an 11, right? Because the that 1 goes in the ones position. I also see that somebody had a 15. I don't know the actual state. I know the actual value. What's the advantage of a stem plot over a histogram? With the stem plot, you have the data. You didn't lose it. Right? I know there was a 15. I know there's 2 15s. A 16, a 17, an 18, a 19, a 75. I've got all the data there. Now, I got to come over here and see if I can screw this up here. I need to find this file. The file here is this example. And I need the one about 1/8, minority. Look, it's just everybody we just talked about there. Could I make a histogram of this data? Yes. I want to show you stem and leaf. So, stem plot, Minitab calls it stem and leaf. It wants to know where your variable is. Same as before, right? What are you graphing? Now, before I start moving anything or doing anything, I want to see what it does for me. Now, here's the problem. Instead of it opening a new window, it puts it there. And you notice it did some crazy shit, right? It wrote down 0, 1, 1, 2, 2, all this kind of stuff. It's like it did something weird with how it made the stems. My question is can we fix this? Increment, 10. I want to go from 0 to 10 to 20, right, like we were doing it in the textbook here. That's the one we want. That's the one that's in the margin on page 30. Okay? Was there anything wrong with the other one? No, not really. Now, does the stem plot show you the distribution of your quantitative variable? Does it show you what values the variable can take, and does it show you how often it takes them? And the answer is, yeah, right? Remember, that's what these pictures, these graphs are supposed to be doing. Notice, Minitab even knows to keep track of the leaf unit. The ones position, right? So that I can recover the data. Now, do you think a stem plot has a shape? Yeah, but the problem is, I have to look at it like this. Because the way I'm thinking about it is this. If I could pick my little screen up, I would rotate it 90 degrees. And then the stems are like on the x-axis here where the value of the variable is, and then the leaves are making up, in a sense, the height of the bars from my histogram. So if I looked at this one and I had to ask you, what's the shape? Well, I can't just look at it like that. You know, I got to do this shit here, and things are looking a little bit skewed to the right, yes? Single peak, a little bit skewed to the right. Everybody follow that? You agree with that? Now, before I tell you about the center, what are you going to tell me about the spread of the variability? What's the smallest and what's the largest? The smallest is 8, right? 0.8. What's the largest? The largest is 75. Yeah? Okay. Now, Minitab also helps me here trying to find the center. You see these numbers all the way to the left? See, those are your stems. 0, 1, 2, 3, 4, 5, 6, and 7. You see these numbers right here? 3, 10, 23, 9 in parentheses, 19, 11, 4, and 1. It's counting both directions. And what it's counting is the number of observations. Notice there's 3 on the first row. There's 7 on the second. It gives me 10. Right? There's 13. Gives me 23. So in other words, from here up, there's 23. From here down, there is, what, 30, 35? Right? That's what it's doing. Well, what it's really trying to do, and what it's really trying to help you do is, you see the one with the parentheses? Around the 9? It's trying to tell you where your center is. It's trying to tell you the one that divided us into half and half is on that particular stem. Right? It's in the 30. That's what it's telling you. Right? The parentheses is telling you, there's 9 on here. It's trying to tell me that I'm looking at the 1 there. My center must be somewhere in the 30%. Right? So in other words, my center is somewhere between 30 and 40. And it'll do that to you every time. Minitab will give you this count going up, count coming up this way. Wherever the parentheses are, that's trying to tell you where your center is. My center here is somewhere between 30 and 40. And I'm going to leave it at that because I did the same thing to you before. We saw that the spread was from 8 to 75. I got any possible outliers here? Oh, I know there's no gaps. I know there's no outliers that I would consider on the low end because I'm looking at what? 8, 8, 9, 11, and so forth, right? What about between 67 and 75? Remember, 67 was California, 75 was Hawaii, right? Are there any outliers there, maybe? And I'm going to give you, I understand there's no gaps. I understand that. But you're off by 8. 8 percentage points. I just want to point out to you that it's Hawaii. Does it make sense why such a large percentage of Hawaii's population is minorities? They don't want a freaking eye. I know there's no gap. I'm just pointing out that when I get to chapter 2 and I can calculate things, even though there's no gap, from 67 to 75, I mean, you're looking at 8 percentage points, something might be up. Okay, that's all. To be honest with you, if I was sitting here looking at this and not even thinking about what's coming, I would have just told you, oh yeah, it looks like it's a little skewed to the right, looks like it's single peak. The center is somewhere between 30 and 40 because of where the parentheses are in the 9. I see the smallest is 8, the largest is 75, and I'd be telling you I don't see any outliers. Just because why? Because there's no gap between the stems here. Right? There's no blank stems. Sometimes it's possible to have blank stems. Okay? Are we okay with this? So I interpret this the same way I would interpret a histogram. Except I have to look at it from the bottom, from left to right, because that makes me think about the bottom of my histogram. These leaves are making the heights of my bars for me. Now, turns out, Minitab always makes a good choice. See, I wasn't upset with this one up here either. You know, with the one they gave me. I know it did something funky here, but I wasn't upset with that. Normally, I would just let whatever Minitab gives me, I would just go with it if I'm going to make a stem plot, right? I wouldn't even think twice about it. I guess my thought is this. And we need to have just a little talk about this, because Minitab may do something screwed up, and then we may have to fix it. It turns out, with a stem plot, you can have, you remember we talked about this with histogram? Where I had a skyscraper. In other words, I had too few stems. Remember when I had too few classes, I made the class widths smaller, right, to make myself more classes with the histogram. Well, here, what we're going to do, there's a technique for fixing this. And actually, Minitab already used it on me and you. It's called splitting stem. What we're going to do is we'll double the number of stems. So I'm going to give you like a quick example just off the top of my head. Let's say we went through and we've got this data and we've made, all my stems and my leaves. And what happened is, when I was all said and done, I only ended up with 2 stems. And I got all these values. All right? So I got all those leaves there, and then I have all these leaves here. Well, so when I look at it, that's like having everything in 2 classes in a histogram, right? That would be a skyscraper. So what we're going to do is we're going to use this technique called splitting stems. The best it's going to do for me and you is we're going to write down every stem we have, and we're going to write it down twice. So we just double it. The first stem gets all the leaves, digits 0 through 4. So I would put 0, 0, 0, 1, 1, 4. So this gets 0 through 4, and this one's going to get 5 through 9. So then when I put the 5 through 9 on there, I'm going to get 5, 6, 6, 7, 7, 8, 9, 9. At least we're spreading the crap out a little bit. And then the first 13 gets all the leaves on the original 13 with all the 0 through 4. And the second one gets all the digits 5 through 9. Right? So again, 0 through 4, 5 through 9. We've doubled the number of stems. We spread stuff out a little bit, and things are starting to look a little roughly symmetric to me. Now look, I didn't throw this away over here. I'll come right back to this. Do you want to know what Minitab was going for us there? What? There's only 1 0, but there's a 1 and a 1, a 2 and a 2, and 3. It split stems for you immediately. All right, it went by. You think about how it did exactly what I said it would do, right? The first one gets the digits 0 through 4, the second one gets the digits 5 through 9. Does it look skewed to the right there? Yeah. Does it look like there's some possible outlier or outliers? And the answer is, yeah, this time we do. Right? That's what it did. Minitab just automatically looked at the data and said, shit, I'm going to split the stems for you. Down here, I fixed it so it didn't. That's the technique for fixing things where it looks like you have a skyscraper where you want to spread stuff out. At least we spread it out there. Again, I would let Minitab do whatever it wants. I will never ask you to make a stem plot by hand. And if it is, it'll just be something really quick where the data is already in order for you. You just make it like in 20 seconds. All right? Now, so this is where you had too few stems. Well, what happens, and Minitab will not take care of this problem for you. Suppose you have a pancake. Remember, with the histogram, everything was all spread out. I had too many classes. Here I have too many stems. How do we fix that? Before, what we did, we made the class width larger, right? Well, here, all we can do is round off. Here's what I mean. Just for the sake of things, suppose I have, let's say, 20 individuals in my data set. Okay? And so that means I got 20 values, and it turns out that the lowest one I have is 126. And the largest one I have is, I'm going to give you one in the middle. There's one in the middle here of, now obviously there's 17 more. The 17 more are between 126 and 982. I just gave you the one in the middle. See, my problem is if I start making stems and leaves here, the blue is the leaf. Right? So my stems are going to range 12 through 98. That means I have what here? 88, 89 stems? This shit only got 20 pieces of data. I got too many stems here, right? Way too many. So what we're going to do is, I'm going to round. Now, how would you round 126 in the normal world? When I say normal world, like, okay, so I'm not going to do anything crazy here. I'd round that to 130, right? 450, 980. Everybody okay with that? That's the way you normally round up or you round down. I don't need those zeros. Here's going to be my leaves. There's going to be my stem. This time my stems range from 1 through 9. How many stems am I going to have? I'm going to have 9 stems, 20 pieces of data. Things seem way better here. How do I keep track of this part I have in green where all of a sudden I just round it off and mark zeros off? What's my leaf unit here? My leaf unit is tens. Right? My leaf is actually in the tens position. So when I go back to my stem plot, I'm going to have this stem of 3 and a leaf of, a stem of 1, a leaf of 3, a stem of 4, a leaf of 5, a stem of 9, a leaf of 8. When I go back to recover the data, I'm going to recover 130, 450, 980, right? I'm going to recover up to round off. I'll never get back to 126, 453, but I can at least get back to where I rounded it off. Okay? Now, are we all right with this? Look, normally I'm more like a histogram kind of guy. I don't know. It's just me. The last thing in this chapter. All right? And I just want to mention it and like give you a little feel for it. The last thing in this chapter is something called time plots. Now, I'm going to scream at you about this for a second. Remember, a histogram shows you the distribution of a quantitative variable. A stem plot does the same thing, right? The stem plot shows you the distribution of your quantitative variable, right? What's the nice thing about the stem plot? You didn't lose the actual data. But a time plot is kind of like a little different object here. What we've got is we've got variable, a variable, measured over time. And I'm going to do this. What I mean is, over time, is measured over time periods. Maybe every day, maybe every week, maybe every month, maybe every year, hell, maybe every 5 years. But the thing is, we have some variable, and it is measured over time at some set intervals of time. Okay? What we're interested in, in how the value of the variable changes over time. So there's a graph for this. And I'm going to give you, obviously the graph is a time plot. Now, here's the way this gets set up. I'm going to show it to you by hand. When we come back Thursday, if I can remember, we'll show you one in Minitab. Now, what happens is a little different. Where the histogram, if I was going to start here, I'd be putting the value of the variable in the x, right? Here is your variable. Down here are your time periods. Let's just say, for the sake of things, however it was measured, I've got these equal time periods. All right? And then whatever the range of values of my variable is, I would chop this up like this, whether by 5s or 10s or whatever it was. So how do you make a time plot is, at all these periods of time down here, maybe it's every month, right? You've got these measured for so many months. So for the first month, you'll have a value of the variable, right? You'll go and you'll find that value. You'll put a little dot. The next month, you'll have a value of the variable and you'll put another dot. The next one. The next one. Next one. So the little dots correspond to the time period and the value of your variable, right? And then what you do is you come back and connect the dots. And so we're looking for patterns in the graph here. Not symmetric, skewed right, skewed left. I'm looking for, I've got three choices here. I'm looking for a pattern that repeats itself, that would be cyclical. You see this one here, how it does this? That is cyclical. Okay? This shows cycles. It repeats itself over time. When you go home and you're reading your textbook, if you will look at example 1.9 in your book, they're talking about water levels in the Everglades, and they pick one spot to measure the water level. And they measure it every month for like 16 years. You know the pattern you see at this monitoring station in the Everglades? You see the pattern I just had there. It's cyclical. Well, wouldn't you expect that to happen? It turns out the high water marks are in February and March, and the low water marks are in July and August. Anybody ever been to Florida? You ever been there in February, March? It actually freaking rains in Florida in February and March, and so the water levels are higher. You've been there in July and August. You don't see no rain. It's 9,000 degrees, and everything evaporates, and the water levels are lower, right? And so over time, you see this pattern, right? High water levels in February and March. High water levels in February and March, low waters in July and August. And it just keeps repeating itself. It's cyclical, right? We like to talk about things that are cyclical, where the pattern repeats, right? It just repeats the same cycle over and over. It doesn't have to be exactly. What I see is it's cyclical, right? It shows a cycle. The other two, I'm not going to label anything for you, but if I'm looking at a time plot, hey, what's going on with your variable here? What's it doing over time? Remember, the variable's on the y, right? And it's going from smallest to largest. What's going on over time? As we went across time here with your variable, the value of it increased, right? This is a upward trend. Anybody got a thought about something meaning you could measure over time that the value of it or the value of the variable increased over time? Oh, no, I always come up with the same kind of shit. What about a loaf of bread? It doesn't seem to ever come back, right? Your electric bill at the house doesn't seem to ever come back down, does it? Over time it increases. Yeah? I know it's time to go to the house. Anybody got an idea what a downward trend would look like? The variable decreases over time, right? So I would see this. Right, so my time periods, and I want to make it obvious that we're going down over time. That's a downward trend. Oh, I know what I could have used for you. College tuition. That wasn't a joke. In case you don't know, that's kind of been an upward trend. And I got my man in the back shaking his head. We know, right? You're paying more and more every semester. They may not call it tuition, but your total bill is going up every semester. Anybody got a thought about something that would be a downward trend? This is a weird thing. The price of a computer. And you're going, really? No. When I first thought about computers, the freaking thing was like $10,000, and then I needed a tractor trailer to get it to my house. Now you use it on the table, and it's like $200, right? What about your favorite technology device, your cell phone? Don't those prices come down over time? Yeah, right? Once everybody gets it. So that's a downward trend. Look, that's what we think about with some now, look, you got to understand, this is different than a histogram. And on Thursday, I'll come back and say this over to you. What a histogram does is it picks one period of time and a whole bunch of individuals and measures your variable. It's called cross-sectional. What a time plot does is it picks one individual and measures the variable on that one individual many times, time series. They're different things for a quantitative variable. They're different graphs. Be careful going to the house. On Thursday, I'll tell you one more time about time series and cross-sectional, and then we're going to pick up and we're actually going to calculate something fine. And it'll look like a math class at least for 10 minutes on Thursday. Be careful going to the house.